तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Look at perturbation theory in a slightly more formal way. You recall that we were looking at Hamiltonians of the form H naught plus some perturbation, and my idea was to show you how you could find the eigenvalues and eigenfunctions of the new Hamiltonian as a perturbation series in powers of this lambda for the simplest case of non-degenerate perturbation theory, where H naught has discrete levels which are non-degenerate. And then we looked at a simple formalism for handling cases when H naught has some levels which are indeed degenerate, and that was the portion where that was a trick whereby you went into the subspace of this degenerate states and then you found the exact eigenstates, and after that proceeded as before. Now today what I would like to do is to put this whole thing on a slightly more general framework, so that even if H prime has explicit time dependence, which is what we would like to handle physical cases, we can still handle the problem. And after we set up the formalism, I will apply it to simple cases such as two level systems, or what happens when you switch on a magnetic time dependent magnetic field for an electron whose spin couples to the magnetic field, and so on, because this will have implications for both quantum optics as well as magnetic resonance and many other areas. So that will be our last topic. Now a formal way of handling this was evolved long ago by Dirac himself in the early days of quantum mechanics, and he introduced a way of writing a transformation which goes from the original Schrodinger representation not to the Heisenberg picture which we already studied, but something in between the Schrodinger and Heisenberg pictures called the interaction picture, and I would like to introduce that. So the interaction picture, and it was a clever trick which tells you in a natural way how to handle problems of all kinds of perturbations, including time dependent ones. So just to recall to you what we had done, recall the original situation for a minute, where we had a Hamiltonian H and we had the Schrodinger picture, and we had on the other side the Heisenberg picture. And for the moment let me just look at a Hamiltonian H naught which is time independent. So in the Schrodinger picture we started with Schrodinger's equation, which is IH cross d over dt, the Schrodinger wave function or state vector, this was equal to the Hamiltonian H on psi s of t, and well, this was the Hamiltonian, which the total Hamiltonian of the system, and that is the equation satisfied by the state vector in the Schrodinger picture. In the case where H was explicitly time independent, you could write a solution which was psi s of t was e to the minus I h t over h cross psi s of 0 for any given state vector here. And physical observables which did not have explicit time dependence in them were represented by Hermitian operators of the form A Schrodinger. There was no time dependence here. So just to recall to your memory, observables did not have explicit time dependence, they were operators, Hermitian operators, and the state vector carries the burden of time dependence and it evolves according to this rule. Given an initial state, you could say what the state was at any time t. This is for a Hamiltonian which does not have explicit time dependence. The Heisenberg picture was a unitary transformation on the Schrodinger picture, and it corresponded to saying that psi Heisenberg was geared in such a way as to coincide with the Schrodinger state vector at some fiducial instant of time which we took to be 0. So psi Heisenberg, which did not have explicit time dependence, was essentially this vector, or if you want to write it in terms of the Schrodinger state vector, it is e to the IHT over h cross psi s of t. In a sense what happened was that the time dependence of this and the time dependence of this cancelled out and you had a time independent state vector. The Schrodinger representation equation was replaced by the Heisenberg equation of motion, and the Heisenberg equation of motion says IH cross d over dt A Heisenberg t was equal to the commutator of AH Heisenberg t with the Hamiltonian. And the solution to this, again in the simple case of time independent H, was simply AH of t equal to e to the power I ht over h cross A Heisenberg at 0, which we said is the same as the Schrodinger operator, AS. Okay. So to repeat what I have said, in the Schrodinger picture the state vector carries the burden of time dependence and evolves in this fashion. Operators do not have any explicit time dependence. In the Heisenberg picture the state vector does not have any time dependence, but the operators have explicit time dependence, and you go from one picture to another by a unitary transformation, because if H is Hermitian, e to the power I times H times a real number is a unitary operator. So this fellow is a unitary operator, U for example, and then psi H is this operator, unitary operator acting on psi S. Similarly the Heisenberg operator is the unitary operator A Schrodinger U dagger or U inverse on this side. So we are justified in saying that the Heisenberg and Schrodinger pictures are unitarily equivalent, they are just unitary transformations of each other. Yeah.
Time independent.
Yeah, now we are going to what, yeah, for time independent Hamiltonians, but I define for time independent Hamiltonians the Heisenberg picture by this trick. Now what we have to do is to ask what happens if there is time dependence in the Hamiltonian. You could still continue to define, you could still say at some fiducial instant of time, even if this has time dependence, you could say that the Heisenberg operator is defined as this operator A Schrodinger at 0 and then this operator again here, but you can still make a unitary transformation, there is no problem, but you can see that it is not very effective to do this if H has explicit time dependence. So what Dirac did was to say the cases we are going to look at are generally going to have a Hamiltonian, a total Hamiltonian of the form H naught, which is time independent and which you presumably can solve, plus the perturbation which we have been writing down H prime, and it is possible that this quantity is time dependent. And then the question is, what do you do? What kind of unitary transformation do you do? This is the problem that you would like to address. Of course there are lots of cases where H prime is time independent and you would like to know what is the perturbation series, etc., but we would like to address the general problem of this kind. Dirac's idea was the following. He said, after all, whether the Hamiltonian has time dependence or not, the Schrodinger Hamiltonian state vector is going to evolve by some unitary operator acting on whatever is the initial state that you give me. Now if the Hamiltonian consists of two parts which do not commute with each other of this kind, there is always going to be unitary evolution due to this portion of the Hamiltonian. Even if you switched off this portion, you still have this all the time. So why carry that time dependence around? Let's get rid of that time dependence. And therefore he said, let us go to an intermediate picture between these two pictures called the interaction picture, and that says that I define psi interaction t in this form equal to, just as the Heisenberg thing had e to the iht psi Schrodinger here, now say that this, you define this to be e to the power I h naught t over h cross psi Schrodinger of t. Define it in this fashion. If you did not have h prime in the Hamiltonian, then the interaction state vector psi I of t is identical to the Heisenberg. Okay. But now I might have an interaction, I might have an h prime. Then ask what happens to this thing here, what's the time derivative of this equal to, what's the equation satisfied by it. So I h cross d over dt, by the way, sorry, defined in this fashion, and for any operator A, define ai of t equal to define e to the power I h naught t over h cross h Schrodinger define it in this fashion. If you did not have, again I repeat, if you did not have h prime, then the I subscript, the interaction, is the same as going to the Heisenberg picture. But notice that you switch on an h prime, you have an h prime, but you still make the unitary transformation using only h naught, the portion of the Hamiltonian that you know. And then what happens? Well, if I write I h cross d over dt psi I of t, this is equal to, I just differentiate this on both sides, and the first term is going to give me I h cross and then I over h cross h naught e to the I h naught t over h cross psi s of t. That is the derivative of this term. I bring down an I h naught over h cross, and it commutes with e to the I h naught, so it does not matter which place I write it, plus I h cross e to the I h naught t over h cross d over dt psi s of t. This is I h cross times d over dt. But I h cross d over dt psi s of t is the total Hamiltonian acting on psi s of t by definition. So this is equal to minus h naught, this h cross cancels, e to the I h naught t over h cross. By the way, psi s of t e to the I h naught t over h cross is by definition psi I of t. So let me write this as psi I of t with a minus sign here, plus, and what is this equal to? I h cross d over dt psi s of t is e to the I h naught t over h cross h naught plus lambda h prime psi s of t. by definition. This is the Schrodinger equation written in the Schrodinger picture. The total Hamiltonian is H naught plus lambda H prime. You still have to be careful to note that this H prime need not commute with H naught in general, and therefore it cannot be brought to the right this side, you can't move this in. Okay. But certainly this H naught can be brought to this side because it commutes with itself, and once you do that, this H naught comes here and you got e to the I H naught t over H cross psi s, but that is psi I, and that would cancel with this term completely. So it gives us an equation which says I H cross d over dt psi I of t is equal to, it just leaves the lambda H prime term, nothing more than that, and therefore it is plus lambda comes out, and then it is e to the I H naught t over H cross H prime acting on psi s of t, but psi s of t is e to the minus I H naught t over H cross. I am going to substitute for psi s of t by bringing this exponent to this guy side here, and it is minus here and then psi I of t. But by definition, this quantity here by definition is the interaction picture represent operator H prime. So finally we get this is equal to lambda H I prime of t psi I of t. See? So we have arrived at a situation where the evolution of the state vector in the interaction picture is governed entirely by the perturbation, which might be time dependent explicitly, we do not care. In this Hamiltonian, this is the perturbation in the interaction picture. So whether H prime is explicitly time dependent or not, we do not care, this is the equation. What about operators? What would operators do? Well, look at an operator which does not explicitly depend on time, otherwise you include partial derivatives. What does this equation give you? This immediately says if I differentiate and put an I H cross dAi by dt, it is the commutator with Ai and the Hamiltonian. So it immediately says with H naught, so it says also I H cross d over dt Ai of t is equal to the commutator of Ai of t with H naught and not H, because if you differentiate it you are going to get this H naught coming on this side and then the H naught on the other side. So what have we achieved? We have achieved a state, a picture, intermediate picture, where both the ket vectors, both the state vectors as well as the observables or the operators representing the observables are time dependent, unlike the Heisenberg or Schrodinger pictures. But the time evolution of the state vector is governed entirely by the perturbation or potential that you apply, and the time evolution of the observables is governed entirely by the free Hamiltonian. So it is in between the two pictures here, and it turns out this problem is much easier to tackle, because this thing here now is very straightforward. You do not have the problem that we had earlier of this being a sum of two operators which do not commute with each other, there is just one operator. Of course it may be time dependent, no problem, we will see what to do about it, but this is now a much neater way of doing things because you have separated the problem. You have got rid of the systematic evolution due to H naught which appears anyway whether or not you have a perturbation. The task now is to actually try and solve this equation. Now how would one do that? Well, many ways of doing this, but if you specify this vector at some initial instant of time, this is a Hermitian operator still, therefore you still have unitary evolution of the system. Then you can write down, given this vector at some initial instant of time, you could choose that to be the state vector, the Schrodinger state vector at t equal to 0. This becomes an initial value problem and you could try to solve this initial value problem by systematic expansion as follows. So let us write psi I of t equal to some unitary time evolution operator t given some initial value, some initial state vector at t0 acting on psi I at time t0, and this t0 need not be chosen to be t equal to 0, we need not do that. All you have to do is to specify for me the initial state which could be a prepared state. I could prepare the system and switch on the perturbation. So we have given ourselves a little more freedom now. We match the Schrodinger and Heisenberg pictures at t equal to 0, but we would match the Schrodinger and interaction picture ket vectors at the instant at which you switch on your perturbation, which could be anything at all. So with some initial ket vector t0, here is a unitary operator, and now the question is what is the equation satisfied by this operator here, and it is not hard to see that this is just Hi on u, so this immediately says IH cross d over dt u of t0. I should really write a partial derivative Hi. Well, I should really carry this around, so let me do that. Lambda Hi prime u The reason I use a partial derivative is because I have introduced this initial time label t0 and I want to make sure that I differentiate with respect to t. Now what is the initial condition that you would impose on this? Clearly u of t0 is equal to the identity operator, because it is clear that if you set t0 equal to t0, t equal to t0, you want the identity operator, okay, and we have to solve that equation for the operator u. After that I plug that into this first line and I tell you what the state vector is at any instant of time. And since the way I would do this is by developing things in a power series, it is clear there is a lambda sitting here, so this will help me keep track of first order, second order, third order terms, etc. But as it stands, this is not a trivial equation to solve, and therefore the first thing you must do is to convert this into an integral equation satisfying this equation, differential equation, and this is entirely equivalent to saying that u of t0 is equal to I minus I lambda over h cross and integral t0 up to t dt dt1, say some fiducial time Hi of T1 T1 with T0, because differentiate both sides after multiplying by IH cross. If you differentiate this guy here, this is constant, so it gives you 0 here, multiply by IH cross, this factor goes away, you get lambda Hi of T U of T with T0 by using the formula for differentiation under the integral sign. The upper limit of integration is a variable, and therefore you would write the integrand at that time multiplied by dt over dt, which is 1. So this differential equation together with this initial condition is equivalent to this inhomogeneous integral equation for you, completely equivalent. And that integral equation can now be solved by the method of iteration, because to order lambda to the 0, u is I, so you put that in here, that is the first order correction here. And you want the next order correction, you put in u to order lambda, which is this formula, and so on. So you end up with a series which says u of T0 equal to I minus I lambda over H cross and integral 0 to T dt1 Hi prime of T1 times I out here, and then the next term is plus so let us I minus I lambda over H cross. You want to substitute for u of T1 with T0 inside there, and therefore it would be exactly the same formula, T0 to T1 some dt2, and then you end up with a u of T2 there. So this would be I lambda integral T0 to some T2 sorry T1 dt2 Hi prime of T2, and what would appear inside here is u of T2 with T0, for which I would again put I and so on. So it is clear that this exact equation gives you an infinite series which is I minus I lambda over H cross 0 to T dt1 Hi prime of T1 plus minus I lambda over H cross whole squared 0 to T dt1 0 to T1 dt2 Hi prime plus etc., an infinite series. Notice very carefully that this operator and this operator need not commute with each other. They have time dependencies and there is nothing to say that they commute with each other, but they are automatically time ordered, because this is the later time and this is the lesser, this is the earlier time, because this integral over T2 runs, sorry, these are all T0s. So it is evident from this that T2 is always less than T1 and T1 goes up to time T. The next term would be a third order term and so on and so forth. Yeah. We are guaranteed, yeah, we made the assumption, we started off by saying H is H naught plus lambda H prime, and we started off by saying that H naught H prime are Hermitian. Lambda is real and these are Hermitian. We started off with that. We started with the Hermitian Hamiltonian. So we have conservation of probability. Yeah.
So you wrote the transformation of the state vector
Yeah.
as the unitary transformation of
Yes.
the initial state.
Yes.
We connected it with the volume preserving flow in the state space, right?
Yeah.
But in the presence of a perturbation,
Yeah.
how are we still sure that the flow will be volume preserving?
We don't know anything about it at all, but the fact is if the Hamiltonian is Hermitian, its eigenvalues are guaranteed to be real, absolutely, whatever the consequences of that be, and that says that the total probability is constant, etc. So in such a situation you can never look at dissipation. So what would happen, however, is if you switch on the perturbation, the total probability would be conserved, but the system, if you start in a given state of H0, given eigenstate of H0, would not remain in that state. It would go to some other state, it would make transitions back and forth, but it does not disappear, right. So the particle, if it's you are talking about a particle in some external field, the particle does not get absorbed or disappear, it just moves to makes transitions from one state to another. So that is the point. There are situations where you might want to put a complex or non-Hermitian Hamiltonian to explicitly put in friction or put in dissipation or loss or absorption and so on. We are not looking at that class of problems. This series is called the Dyson series. It is in a little greater generality than we need to solve odd problems in ordinary quantum mechanics. It is a little more powerful than what you need for that, but the advantage is that this is precisely the series that you use in quantum field theory, for instance, because we have not really made any assumption about what kind of system we have except that it has a Hermitian Hamiltonian, right. And the trick, the ultimate the trick, the way to get the perturbation series explicitly is to convert this differential equation for the unitary operator u into an integral equation, and then it follows by iteration. Okay. Now of course you could ask, does this series converge, and you have exactly the same problems of convergence which we had earlier, which we brushed under the carpet without really looking at it. So you really have to again prove explicitly that this Dyson series converges formally. We are not going to get into that technical question here because this is outside the purview of what I want to do here, but the fact is that this is exact, there is no approximation being made here. In that sense this is a formal power series and I am assuming that it is regular, it converges, makes sense and so on. Okay. So now the question is, can we say something about what the state actually does, can we do this, can we simplify this and write it in the instances we would like to look at. Well, for that what one would do is the following. Instead of looking at this formal time ordered solution, oh one final thing, I pointed out that these operators at different instants of time do not commute. If they did, if you could freely mix this around, then it is clear that each of these integrals, for example take the second order integral here, it runs over two variables, there is a t1 and there is a t2, and each of them runs from some t0 up to t. So this is t0, this is t, this is t0 up to t, and the integration is being done in such a way that t2 is always less than t1. So it is being done over this triangle here. So what you are really doing is fix a t1 between t0 and t and integrate over t2 along this line from t0 up to the current value of t1, and then this and this and this, and you add up these things and you end up with this integral. Okay. Now if we did not have the problem of convergence or anything like that, then this integrand is symmetric under the interchange of t1 and t2. Therefore the value of the integral here is the same as the value of the integral reflected about this 45-degree line. So you could write this as an integral, half the half the value of the integral over the full square here. You divide by a 2 or a 2 factorial. So you write this as 1 over 2 factorial integral 0 to t 0 to t, and then the next one would be 1 over 3 factorial 0 to t for all of them, because if you took 3 numbers t1 t2 t3 and ordered them, there is exactly one way in which you have t1 less than t2 less than t3. You have several other ways of permuting. You have 6 out of 6 combinations, you have one of these, right. So each time you put a 1 over n factorial and you do the integral for each of the n variables from t0 to t, and then of course it is just the exponential, e to the power minus I lambda over h cross t0 to t dt prime h prime of t prime. Now you can't quite do that here because of this lack of commutativity, but you could still time order it. So what you would do is to say, I would still write this as equal to 1 over 2 factorial and integral t0 to t dt1 t0 to t1 dt2 hi prime of t1 hi prime of t2 plus, and now interchange dt2 dt1, and this is t0 to t and this is t0 to t2, but now interchange and you get hi prime of t2 hi prime of t1. That is exactly the same as before, because all I have done is to interchange the labels t1 and t2, and I have taken care of the commutation problem because the earlier time is on the left and the later time is on the right. But this is exactly equal to this, but this I could call, this plus that I could call the time ordered product, in which the rule is put the earlier time argument on the left, the later time argument on the right. So I could write this as the time ordered product t of this guy and erase this, and then I have a 1 over 3 factorial, the time ordered product, etc., and that whole thing can therefore be written as the time ordered exponential minus I over h cross. If this is the time ordering operator, time ordered 0 to t dt prime. This is called the time ordering So this is of great use in quantum field theory. When you write down perturbation expansions, you must remember that the formal solution to the Schrodinger equation, the equation for the time development operator in the interaction picture, is a time ordered exponential, etc. And of course when you do relativistic quantum field theory, the question of can you order time, etc., comes in, and this can be done for the physical processes we are interested in. There are intervals which are space like, where the question of time ordering does not make sense, so causality is brought in and so on and so forth. So it is a very useful concept, this idea is extremely useful, but for the kind of problems we are looking at here, this is a little too powerful, we do not need this, but I thought you should know the formal expression. Okay, now let us do the following. Our task is to find out what is psi I of time t at time t, okay. And I know that it is satisfied by do, this equation satisfies hi of t psi I of t in this fashion, okay. So let us do the following. Let us write psi I of t as equal to, as usual we assume that the unperturbed Hamiltonian H0 has eigenvalues and eigenstates which we know, we call them phi n zeros and E n zeros. So let us expand it in that basis, equal to a summation over n, some coefficients which could be time dependent will be in general, and then phi, I use a symbol phi n zeros. So what is the assumption? The assumption is that H naught on phi n 0 is equal to E n 0 phi n 0, and that they form a complete set and so on and so forth. Okay. Now I can still use the same basis, that is it, that is like fixing a coordinate system once and for all. So I use the same basis, and in this Hilbert space the assumption is the perturbation is such that the states are not taken out of this Hilbert space. There could be transitions, but they are not taken out of this space, and then I can expand any arbitrary state vector in whatever picture you like in that basis with coefficients which would be in general time dependent. Okay. So this is a completely general statement here, and I am going to put that into this here and see what happens. So how do I find out what is Cn of t? This implies of course that Cn of t, by the way this forms a basis, so it implies also that phi m0 phi n0 equal to delta. So it forms an orthonormal basis. Then Cn of t is just this amplitude phi n0 psi of t. Now that of course we know, once you have an orthonormal basis, this coefficient is just the overlap of this state vector with the corresponding bra on this side. So let us put that in and write IH cross d over dt Cn of t. So I take the scalar product on both sides with phi n of 0, and phi n of 0 is a time independent state vector, basis vector, so it becomes d over dt Cn of t on this side, that is equal to phi n 0 hi of t psi I of t. So all I have done is to take this guy here, and I have that is it. Okay. But what is hi of t? Sorry, it was hi prime, right? Everywhere there was an hi prime, and there was also a lambda, so let us keep track of that. Lambda hi prime. This is equal to lambda times phi n 0, and if you recall our definition of this operator here, it was equal to e to the I h naught t over h cross h prime in the Schrodinger picture, just the original h prime, e to the minus I h naught t over h cross, and then a psi I of t. By definition, by the definition of this operator here. What should I do next? Well, it is clear that I need, what I am trying to do is to take this equation, expanding the unknown ket vector in this basis set and converting the differential equation for this ket vector to a differential equation for the coefficients. And of course this is going to be an infinite set of equations for the coefficients, and on the right hand side, since it is a linear equation, you expect a linear combination of the same coefficients with some factor in front, with something or the other acting in front, and the question is what is in front. So what would you do next? I would like to get an equation which involves the Cn's on this side. I am almost there, but I need to convert this state vector into a coefficient. What should I do? What should I insert here? complete set of states. I insert a complete set of states. So it immediately says, we could do it right there. So in here, insert inside here I equal to summation over m phi m 0 phi m 0. Insert that in there. So what does that give us? It says IH cross d over dt Cn of t equal to, now that is just an equation for a function of time, there is no operator or anything involved here, that is equal to lambda times, I bring this summation all the way out, then I have summation over m phi n 0 h prime, what is this operator acting on phi n of 0? Well, we know that it is just e to the power I E n 0 t over h cross, that comes out as a factor outside. So you get the first term is e to the power I E n 0 t over h cross, that comes out as a factor, but what remains inside is phi n 0 and then an h prime, and notice once again that h naught t acting on phi m 0 is going to give you the same e to the I E m 0 with a minus sign. So m 0 minus E m 0 t over h cross, and then phi n 0 h prime phi m 0. So both the phase factors have come out, and you have this matrix element, and it is multiplied by what? By phi m 0 bra vector psi I of t ket vector, but that is Cm of t. Which is equal to lambda times summation over m. Now what would you like to call this? What are these fellows? Well, these are the unperturbed levels, E1 0, E2 0, E3 0 and so on, and what we have here is an energy difference Em0 minus En0 divided by h cross, so it is the frequency, it has dimensions frequency, and I could define this to be, so En0 minus Em0 over h cross equal to omega mm, define. By the way, omega could be negative, if En is less than Em, of course we do not care, so we use, it is an algebraic quantity, so it is e to the power I omega nm t times this, but what is this? This is just the matrix element of h prime in the original basis, so this is h prime nm, some complex number in general. All we do know is that h prime nm is the complex conjugate of h prime mn, that much we know, and then multiplied by Cm of t. So this is my equation, IH cross d over dt Cm. I'll bring this to the other side, so minus I lambda over h cross So we have a set of linear ordinary differential equations for this for the coefficients, and now if you give me the perturbation, these quantities are supposed to be known, these frequencies are supposed to be known, and then what you are doing is solving a matrix equation. Could be infinite dimensional in general, but this would depend on how big these matrix elements are. So if it turns out that H prime does not have connection, does not have a significant matrix element between levels which are very far separated, then you could drop it and truncate it, and in any case there is a lambda sitting here, so you can solve the set of equations again iteratively. So the next trick would be to say let Cn of t equal to Cn to 0th order plus Cn to first order plus dot dot dot, plug it in sequentially and solve these equations. So I would put in the 0th order here, that would give me the first order term, I solve it and then I put it back here, solve it and so on, which would be an operational way of solving that Dyson series in general. But this quantity here is some kind of time dependent matrix acting on these coefficients, and this time dependent matrix would look like, for example, if you write down this matrix element, the 1 1 element, this would be just H prime 1 1, but the 1/2th element would be H 1 2 prime e to the power I omega 1 2 t and so on, and on this side you would get H prime 2 1 e to the minus I omega 1 2 t, so it would be in fact the complex conjugate of that. So once again what is multiplying even with this time dependence is actually a Hermitian matrix, and then you could use iterative methods once again to see whether you can write a solution in series in lambda. So what we are going to do, what I will do next time, is to take this equation and apply it to the simplest possible case, and the case I am interested in applying it to is the following. I have a spin half system, or I have an atom in which I assume that there is just a ground state and an excited state, it does not matter, and I end up with 2 get vectors, one of which is 1 2, that is it, just a 2 level system with 2 levels, either the ground state and the excited state of an atom, or if I put it inside a magnetic field, this would correspond to spin down and spin up states, for example. Whatever it is, this has some energy E1 0 and this has energy E2 0. So that is my unperturbed system. I prepare the system in one of these 2 states, and then I switch on a time dependent field, and the field I have in mind is the following. So there is some separation, natural frequency here, some energy difference H cross omega, this is omega 2 1 if you like, and I switch on a perturbation at a different frequency. So I add an H prime of t equal to some lambda and then some constant e to the power I omega t, this is omega 1 2. And I switch on a field at some other frequency, and then I would like to know what happens as I tune omega over different values. For instance, if omega exactly equals omega 1 2, what happens? Then it is in resonance. So this is the problem we are going to look at, and I will show you that there occur what are called Rabi oscillations in this problem, which is of significance in many physical applications, and the one I am going to look at specifically is a magnetic resonance, for instance. So the idea is I apply a huge field in the z direction so that I have 2 possible states of the system, and after that I apply a field in the transverse direction as a perturbation, which would cause, as you know, flips between up and down, but now I am going to apply a time dependent field, and this is typically what is done in an NMR experiment, where you align with a static field, a large static field, and then you apply a transverse radio frequency field and watch what happens to the system, and we will see that there is a rich amount of physics involved in this. So this I will do tomorrow, and that will be our last application. I will also mention the connection with a similar model for radiation for atoms in the presence of radiation. It is essentially the same physics once again. So each time we need to write down a model Hamiltonian, a model for the perturbation, and then ask what happens to the transition rates. In particular, we would be interested in calculating what these quantities are, because modulus Cm of t whole squared is the probability that if you start, remember this whole thing is with some given initial condition. So this is the probability that at time t the system is in the eigenstate phi m of 0, phi m 0, and that will change, and we would like to see how it oscillates. Now we saw this a little bit earlier when we took the spin half system and just applied a static external field in the transverse direction, but now we would like to apply a time dependent external field, and then there are now two time scales to play with in the problem, one of which would be the energy difference h cross omega, that gives a natural frequency of the system, but there is a second time scale coming in from the frequency of the driving force, and we would like to see the interaction between these two time scales, see which one dominates in which regime. Okay. So that will be the next topic we do. Let me stop here today.